Okay, it's setting up. I will wait 2 seconds after the YouTube side is ready. Okay, the YouTube live streaming is on. So first, I will start with a brief introduction to our speaker today, Dr. Vasant Sanjay. Dr. Vasant Sanjay is currently a postdoc researcher in the physics of fluid group at the University of Kent. So he specializes in using direct numerical simulations to explore several interfacial and free surface flows, especially this involving drops, bubbles, jets, and complex fluid flows, such as plasto-capillary flows. So he obtained his bachelor's and master's degree in mechanical engineering from the Indian Institute of Technology, Roorkee, in 2018, and later obtained his PhD in applied physics from the University of Kent in 2022. And Dr. Sanjay, and please start your presentation.
Yeah, thanks a lot. Thanks a lot for a lovely introduction and for inviting me here. So today I'm going to talk about drop impact. And before I begin, I would like to first mention my collaborators, which are on this slide over here. All the people who are in bold, so I'm going to present work that I did with them. So first of them, it's Detlef Loze, who is my PhD supervisor and also a very close collaborator. And we also have this work in collaboration with Tsinghua University and University of Twente as well. And there's also a color code, which is some people are in orange and some people are in blue. I'm going to disclose the color code towards the end of the talk of what it means. So with that, so today I'm going to talk about drop impact. And to introduce what I will be showing you for the next 40-45 minutes, let me start with this video. So this video was shot by Scott Kelly, who is an astronaut, and this video is taken at the International Space Station. And what you see Scott doing here in this video is that he's playing ping pong with a water droplet. So he's holding these two superhydrophobic paddles and he's just playing ping pong with it. So when we see this video, there are several questions that we can ask as physicists. The two questions that we decided to ask are these. The first one is how much force does Scott have to apply on these paddles in order to keep it stationary? So essentially, what is the force of impact between the droplet and the paddle? And the second is when will this impacting drop, the one that you see going up and down, when will it stop bouncing? So today I will share with you these two stories. So let's dive to story number one, which is this one. So which is the drop impact forces, which was recently published in PRL, which is this article over here. And what we have is something like this. So if we draw it schematically, so that's what you will get. Basically, you have a spherical droplet with diameter d0 and velocity v0 falling on this super hydrophobic substrate. And there is surrounding medium with a surrounding density rho s and viscosity eta s, and the drop density and viscosity are rho d and eta d respectively. And we also have a surface tension between the droplet and the surrounding. And using these control parameters, we can define several dimensionless numbers. For example, we could have a Weber number, which is nothing but a comparison between the inertial stresses as compared to the surface tension stress. So that gives you the Weber number. We also have something called an Onezog number, which is over here, and this you can think of this as a dimensionless viscosity, because it pretty much tells you that how much viscous dissipation is there inside the droplet. And we also have correspondingly an Onezog number of the surrounding and the density ratio between the surrounding and the droplet, and we are going to keep these two numbers fixed so that we have a free surface. Essentially, it's so that the surrounding medium does not influence the drop impact process. So with that, next I come to my simulation methodology. So I won't talk about this in detail today. What we do is we use a volume of fluid finite volume method solver with Basilisk C, which was written by Stefan Popp and his team, and basically the entire documentation is there on this link, and you can also follow this sandbox where I share my codes with the community here. The only thing to remember is that the way we will model these droplets is on a superhydrophobic surface is by assuming that there will always be a thin air layer between this droplet and the superhydrophobic surface. So that's one information that you need to know. Otherwise, most of it is very standard. So let me give you some context of why we are studying this process. So I introduced these two numbers, Ohnesorg number and Weber number, in the previous slide. And essentially, if we think about rain droplets, for example, the rain droplets lie in this range. And of course, it's important to study them, and it's important to know how much force they impact they have once they impact surfaces, because that will lead to things like erosion and so on. So that's very crucial to understand this regime. For example, the second regime is also something like basically which is very important for industries. For example, this inkjet printing, and that lies between, let's say, Ohnesorg of 0.1 to 1, and in the Weber numbers in the range of 100 to 1000 pretty much. So it's also relevant in the context of industries. And the third one, which could be somewhere in between these two regimes, is this jet droplets that come out of bursting bubbles, which are these ones over here, and they would lie in somewhere in this green regime. So first today, in the first story, what I'm going to do is I'm going to fix my Ohnesorg number to this value. This value is special because this is the Ohnesorg number that you would get if you have a water droplet which has a radius of 1 millimeter. And if you would calculate the Ohnesorg number with this definition, you would get somewhere close to this value. And that's why this Ohnesorg number is quite special. And we are going to fix this Ohnesorg number, and we are going to look at our process in the parameter space of Weber number. So fixing Ohnesorg, and we go in this horizontal x-axis. Now let me show you one typical case that I'm going to show over and over again in this today, and that's this one. So we have this droplet that impacts on a superhydrophobic surface. It spreads and then it takes off. Two things to remember is on the right hand side, I'm plotting the velocity field magnitude normalized with the impact velocity. So if it is 1, which is dark blue, then you get velocity of 1, which is at t is equal to 0, as you can see. And on the left hand side, I am plotting log 10 of the viscous dissipation function. And we do it on a log 10 scale in order to contrast regions of high viscous dissipation and regions of low viscous dissipation. So with that information, let me play this video once again. And you can really see, so wherever you have black regions on the left, those are the regions of high viscous dissipation. So that's a typical drop impact process. But what we want to do in the first case is to measure the force that these droplets have on the surface. And for that, in the experiments, we have this core sensor which measures the force. All these experiments, by the way, was done in Tsinghua University by our collaborators, Bin Zhang and Kungjing Li, and they have done a very nice job of getting us this data from there. And in the numerics, it's rather let's say simple to calculate these forces, and that's by taking this pressure integral at the surface, and that will give you a force. So without further ado, I will show you a direct comparison between the two cases. So in this video, there are no fitting parameters. We have the same Weber number on the left in the experiments and on the right in the simulations. And the blue line on this plot is from experiments, and the red one is from simulation. And you see a very nice agreement between the two. And so we were quite happy about this result. But what we wanted to do is to understand the different parts of this curve. So for example, we have this first peak. So the moment of impact that translates to this first peak, which we call F1, and the time it takes from the impact until this first peak is achieved, that we will call by T1. And then of course, this peak goes down. And once the droplet is at its maximum spreading diameter, that's when the forces go to a very small value. And so the first question that you can ask is what sets F1? So how do we know the magnitude of this peak, the peak F1? And for that, I want you to look at these two images. So one is at t is equal to 0, just before impact. And the second is t is equals to T1, that is the instant of this maximum force on the surface. And what is quite interesting that we see in this on these between these two figures is that at t is equals to t1, most of the droplet here is still falling down with the same velocity v. So you still see it's all blue over here. So it's very close to this velocity of v naught essentially. Which means that if we want to calculate this force, we have to take the rate of change of momentum of this droplet. That would be like dt of mv. But since most of the droplet is still falling down with this velocity v naught, in terms of scaling arguments, we could say that this force is nothing but the rate of change of mass. So the mass flux times this velocity of impact, that is v naught. And this dm dt, again, once again, it's just a mass flux, right? So we can just write it as density times velocity and times d naught square, because that gives you like an area. So d naught square gives you an area scale, and rho v naught gives you the flux of this mass coming down, and that times the velocity, that gives you some sort of force scale. In fact, this is something that we call the inertial pressure force that you can see over here. So what I have done here on this slide is just walked through quickly walked through a simple scaling argument. But if you want to get more details of it, and if you want to really also calculate the prefactor that comes in this scaling analysis, I guide you to this paper from Leonardo Gordio in this JFM, which is a very nice work where they use some sort of a modified Wagner theory to actually calculate this more rigorously than what I have shown you over here. But what we can do now is plot this f1 compensated with the scale that we found in the previous slide, and plot it as a function of Weber number. And now what you see is these are the simulation results, that we do end up at a plateau over here in the limit of high Weber numbers. And we are also quite happy because also the experimental results, they also lie exactly on this curve that you see. And you would notice that there is this deviation on to when you go to small Weber numbers, and those deviation come in because at small Weber numbers, the force scale, the pressure scale inside the droplet, it's not inertial, but it's capillary. So in this scale, we would say the force actually scales with gamma times r, and that's why there is this deviation. And if you would try to rationalize this by making some sort of fit, so basically, if we are in the low Weber number range, then this term will dominate. So this force compensated in this way would give you 1 over Weber scaling, which you see over here. And in the high Weber number limit, we get this dimensionless force that goes to 0.81, and this is something that Leonardo Gordio found, let's say theoretically, in his paper, and we found it using this curve, and also using some scaling arguments. But then moving on, the second question that you might wonder is when will this F1 occur? So what sets this T1, which is interesting. It's basically set by this inertial time scale, that is d naught over v naught. And in this plot that I'm showing you here, I have chosen, instead of compensating this time with this inertial time scale, I chose to compensate it with the inertial capillary time scale, and the reason for that will become clear in the next slides. But for now, let's see what happens if we have this time compensated with this inertial capillary time scale. Then this T1 scales basically as 1 over square root Weber in these time units, and that you see very nicely is depicted in this plot over here. In fact, this solid black line that you see, that has a exact solution of 1 over 6. That once again comes from this paper by Leonardo Gordio. So that was the story about the first peak, which is intuitive. It's the first peak which comes in because of the impact, the inertial impact of this droplet. But what happens when we move on in time? So when we move on in time, we see this second peak in the force, which is this F2, which happens at T2. And when you think about it, it's quite intuitive to realize why there should be this second peak. And that's because we are impacting these droplets on super hydrophobic surfaces, which means that these droplets are going to take off. And when they take off, they will apply a force on the substrate. And that's what we see here. That the signature of this takeoff or this motion upwards of the droplet, we see that as this F2. And then if we wait long enough, then this drop will completely detach or completely take off from the substrate, and this force will go to 0. That we also see happening at this time T3. So this is essentially the summary of what we just saw. And the next question that we can ask, looking at this plot, is similar to what we did for F1, is we can ask when, like, first of all, when this F2 occurs. So basically, what sets this T2? And the second question that we can ask is what sets the magnitude of F2? So there are two questions once again that we can ask. So first is, when does F2 occur? And for that, let me quickly walk you through this drop impact and spring mass analogy, something that was proposed in this very nice Nature paper in 2002 by David Curray and Christopher Claney and Dennis Richard. And they basically say that this drop impact is analogous to one drop oscillation. So the only difference between like an oscillating drop and a drop impact is this presence of this substrate that is going to create this asymmetry in this drop oscillation cycle, which means that the time period of drop impact should be equivalent to this Rayleigh time period of drop oscillation, which is given by this inertial time scale, given by this inertio-capillary time scale. And that's why I chose this is time scale also in the previous slides, by the way. So if we look at this process, so what happens is, once we have this drop impact, the drop impacts and spreads, and this impact and spreading, we can think of it as 1/4 of the drop oscillation cycle. So that's the impact and the spreading part, which you see over here. And in fact, if we plot Tm, which is the time at which the drop reaches its maximum spreading diameter, it indeed saturates when we compensate it with this inertio-capillary time scale. And in fact, it goes to this Tc/4, which is Tc is the total time cycle of drop oscillation, and Tc/4 is essentially the 1/4 of that cycle. And then what happens is, once this drop is in the state of maximum spreading, which is at Tm, it's going to retract because of surface tension. And when it retracts, at some point, the motion of this droplet will go from being predominantly in the radial direction as it is retracting to being predominantly in the axial direction that you can see over here. And that the signature of that would be the formation of this Worthington jet that you just see in this video. And that will be between Tm and T2. And in fact, that also takes place in 1/4 of this drop oscillation cycle. And by the way, this is also the time instant at which we have the maximum force on the substrate. So and that we can think of it is because of this formation of this jet that forms because of the converging flow field as the drop is retracting. And at some point, this flow goes from being in the radial direction to being in the axial direction, and that leads to this the second peak in the force, and that happens precisely at half drop oscillation cycle. And once we move on, then now we have a substrate, right, which will create an asymmetry, and that is going to disturb this symmetric drop oscillation cycle. And as a result, what we see is that the other half, so this 1/4 will give you half of the drop oscillation cycle, and the other half goes entirely into this elongation and takeoff phase. And in fact, these droplets take off looking like a bowling pin. So if you ever go to a bowling alley and you play this game, you see that the bowling pin also looks very similar to the droplet that I'm showing over here, and that's how they take off. And all of this you can find in this very nice paper. So that was the answer to the question that when does this T2 occur? So that we know now. But the next question is, what sets this F2? And in fact, we can plot that F2 as a compensated in this inertial time scale, again as a function of Weber number, and we get something like this. And I'm going to walk you through this different shaded regions in this plot. So for example, the first regime is the capillary regime, which is in this brown region over here. And what happens here is that there is not just two peaks in the force, but actually there are multiple peaks. And the reason for this is because of capillary oscillations. So let me play this once again. So what we have is the pressure inside the droplet is capillary, and we have this multiple modes of this capillary oscillations that leads to this multiple peaks on the impact force. Then if we move on, Then we go to the second regime, which is a singular jet regime, which is over here. And I'm going to show you, because at some point this force increases and you see it over here. And I'm going to show you the video, which is for this highest peak in the second impact force. And that I am showing over here. So once again, as the drop impacts, we have this F1, which is over here. By the way, one difference between this case and the previous case, you can see by looking at these capillary waves that occur over here. And this is the instant of F1 in this case. And then what we have is something called a pyramidal droplet. And that once again is because of these capillary waves that you see on both on the force plot, as well as in this droplet over here as well. So you see it at both places. And then moving on, we get this air cavity, and this happens because these capillary waves, which were traveling on top of this droplet, they converge, and then they create this air cavity over here, and then this air cavity would collapse, leading to a singular jet. And this is a reminiscent of a hydrodynamic singularity that occurs because of converging capillary waves. And if the convergence is sweet enough, so if it is, it's basically it's a resonance. So if the convergence occurs at exactly at a sweet point, so if it happens precisely as you see over here, then we get this singular Worthington jet that leads to this second peak, and that this second peak is both sharper as well as 3 times higher in this case as compared to the first one. So it's possible to have a second force peak, which is thrice as much as the first one that you can see over here. And that happens at this F2, and it happens in a very narrow range of Weber number that I will tell you in a minute. But once we again move on, so then it takes off, and then the force goes to 0. And another signature of this regime is that we get this bubble that is entrained inside this droplet because of these converging capillary waves. And that then it takes off pretty much. So I will just play this once more, and you see this this nice agreement once again between experiments and simulations. So the question naturally arises is what sets the boundaries of this regime over here. So let me show you 3 movies. By the way, this regime, as I said, is very narrow. So in fact, the moment you go to this Weber number of 5 or to this Weber number of 12, we see 2 things. One is that the bubble disappears, and second is that this second sharp peak that we saw for Weber 9, it gets blunted out, and you see it doesn't go as high as compared to the in these two cases basically. This is because this Weber 9 is really this resonant Weber number where the capillary waves are they converge at exactly at the sweet let's say instant when we get this hydrodynamic singularity in this drop impact case. And that sets this these boundaries. And the third regime that we get would be the let's say this inertial regime, where once again this force compensated with the inertial pressure force is a constant that you see over here. And the constant the prefactor in this scaling is 0.37 that we find from our experiments and simulations. And one way to rationalize that is basically if you look at these 2 cases. So one of them is at Weber number of 100, and one of them is at Weber number of 30. What we see is that the Worthington jet, it becomes it gets thinner, but at the same time it also gets faster. And as a result, the momentum that it carries, it remains the same in this dimensionless space. However, I mean the two morphologies are quite different. But what happens next? What happens next is a case where we have a very stark disagreement between experiments and simulations. So you can see here that the experimental data points they start to fall down, whereas the simulation data points they remain on this inertial regime, which is this plateau that we found out. And the reason for that is drop splashing. So if I show you this video now, so on the left hand side we have this drop impact spreading. This is Weber number of 225, and what you see is this droplet, because of this splashing and the breakup, basically breaks into these daughter droplets, and that takes away some of the momentum when you are in this when we do the experiments. However, in simulations, we assume an azimuthal symmetry. So basically, we assume that the simulations are axisymmetric, and there is no azimuthal instability that would break this droplet apart. And as a result, we still are operating in this inertial regime. So this disagreement that we saw on the slide over here, that's nice, because it helps us to understand the physics of why this force goes down in experiments, and that is really because of this breakup of droplet, because of this azimuthal instability that you can see very nicely over here. So in summary, for the first, let's say, part of my story, we looked at this force as a function of time, and we identified these two peaks. We also tried to understand that when do these peak occur. So when what's T1, what's its T1, and what's its T2. At the same time, we also looked at their magnitudes in this Weber number range. And just before I go on, basically we asked one question in the beginning, is how much force is Scott Kelly applying on these paddles? And as it turns out, the force that he's applying is proportional to this inertial pressure force. And if we were to normalize this force by the weight of this droplet on Earth, so of course when you are on the International Space Station, then G goes to 0. But if we are on Earth, and if we normalize this impact force with the weight of the droplet on Earth, then, and if we fill in some numbers, then basically what we end up with is that Scott is applying a force which is 100 times more than the weight of the droplet on Earth in order to play this ping pong with the droplets. For more details, please feel free to read this paper, reach out to me, and we can have a discussion about it in detail. So that was the first part. So how much force is being applied on this droplet as it falls on a superhydrophobic surface. The second one is, when does an impacting drop? So when we have such a case, a drop falling on superhydrophobic surfaces once again. So when will this drop stop bouncing? And for that, basically, I remind you what the context was. So essentially, now we are asking under what conditions will this drop stop bouncing from these paddles? And for that, once again, we have this the same set of schematics. So basically, drop falling down with velocity v0, viscosity and density as eta and rho. Of course, we have a surrounding as well. And in this case, we also consider gravity, because we also unlike Scott, we wanted to do these cases also on Earth. So we wanted to also have gravity included. And then we have this Weber number, which is inertia versus capillarity, Ohnesorg number, which is a dimensionless viscosity, and bond number that comes in because of this inclusion of this gravity, and that's gravity versus surface tension. And of course, we have these two Ohnesorg numbers and the density ratio, which we are going to keep fixed once again in order to have like a surrounding medium that doesn't influence the drop impact process. So before I move on, I'm going to spoil it already. So the way the droplet can stop bouncing is because of two reasons. One is a viscous inhibition. So if the drop is so viscous that whatever energy we put in inside the droplet, it gets dissipated the moment it impacts on a surface, then the drop will not bounce. And the second way it will stop bouncing is because of weight inhibition, which is if the drop is very fat or very heavy, then the drop will not bounce. It will be unable to take off from the surface, as since we are doing these experiments or these calculations on Earth still. So let me give you the first one. So first one is this very nice paper from once again from David Carey's and Christopher Claney's group. And what we see here is that water droplet that falls and then takes off on this surface. And if you increase the viscosity of this droplet 1,000 times, which is this case, so basically they do it by adding glycerine to the droplet, then the droplet stops bouncing. And as I said, it's essentially controlled by Ohnesorg number, because Ohnesorg number is nothing but the ratio of the viscous dissipation scale as compared to the impact kinetic energy. And if that ratio is of the order of 1, then the drop doesn't bounce. And that you can see in this between these two cases over here. And so the critical Ohnesorg number is somewhere close to 1 in this case. And that I rationalized by showing you this video, this simulation that we did. And once again, on the right hand side, I'm showing you velocity normalized with the impact velocity, and on the left hand side, I'm showing you the log 10 of this viscous dissipation function. And one interesting feature, which is in this simulation, which is quite different than the previous ones, is that now viscous dissipation is not localized, but is actually happening in the throughout the bulk of the droplet. So the moment of impact is we can correlate that with this very high viscous dissipation. So the entire region was essentially black at the moment of impact. That leads to a very high viscous dissipation at impact. Of course, the second way of not bouncing would be because of the weight of the droplet, and that is controlled by this this bond number. You can also think of bond number as a dimensionless weight of the droplet, and that can happen in this fashion. For example, this is a case with bond number of 0.5, and this droplet very nicely takes off from the surface. Whereas if we increase the bond number to 4 now, so this bond number is 4, we see that the droplet cannot quite take off from the surface, but rather it stays on the surface, and it undergoes these surface oscillations, and it will keep on oscillating. If I let the video or the simulation run longer, it will keep on oscillating until the entire input kinetic energy to the system is dissipated by viscous stresses. But the drop still doesn't take off. It does it by just keep doing this surface oscillations. So in fact, as it turns out, the critical bond number beyond which the drop will stop bouncing is this bond number of 1 that you saw in the previous slide. And so in this case, we have the two control parameters that we care about are the bond number and the Ohnesorg number, and that's the parameter space over here. And just to summarize what I showed you in the previous slides is that if we go in the Ohnesorg phase space, we can stop this drop from bouncing once we go beyond this limit of Ohnesorg of 1. And that's this one over here. And if we explore this parameter space on the y-axis, then we can stop the drop from bouncing once we are beyond this critical bond number of 1 once again in this space over here. So this is the summary of the slides that I showed you just now. And in fact, if you were to plot the two experimental papers that I showed you in the previous slides, the data points, they lie quite nicely on these two asymptotes over here, as you can see. But the question naturally arises that what happens here? So what happens in between these two asymptotes? And we sort of learned it the hard way around while we were working on this other paper, where as it turns out, in our system, the bond number and the Ohnesorg number was not close to either of the asymptotes, was actually somewhere in between. And that would happen if in the lab tomorrow, if you go to the lab and do experiments with a silicon oil droplet, then you could explore the parameter space that is in between, and that happens if you have a 1 millimeter radius silicon oil droplet. And this data point is what led us to explore what happens in between these two asymptotes. So for that, let me show you these three cases. So now basically what I do is that in all the three cases, both the bond number as well as the Ohnesorg number are smaller than 1. So all the three cases, they lie inside this regime that you would, by looking at the asymptotes, that you would think should allow the droplet to bounce off. However, as you can see over here, is that both these red data points, they both cannot bounce off, and that's the reason why you want to understand what happens between these two asymptotes over here. So the first part that occurs is basically drop impacts, and then it reaches this maximum spreading diameter. And by the way, what we found quite interesting in this case is that once the droplet is at its maximum spreading diameter, as you can see between these three cases, the velocity field inside the droplet is pretty much negligible. So the droplet doesn't really have any velocity, like internal kinetic energy as such at these instant. Furthermore, what we also saw is that the maximum spreading diameter of the droplet between these three cases is pretty much the same, and that led us to make one key assumption as I describe the next steps in the next slides. And that key assumption is that we are going to assume that from now onwards, from this stage onwards, the drop has forgotten all about the initial impact. So it doesn't remember the impact velocity and so on. And that's because currently right now, the internal kinetic energy of the drop is negligible, and the maximum spreading diameter, that's the surface energy difference between these three cases, that's very close to each other. And then what happens is that now we have a system, we have a pancake pretty much, and which has a high surface energy, and that is going to retract, and then it will try to take off. So what we have is a decoupling between the two processes, the impact and spreading process, that's part one, and part two is this retraction and takeoff, and we have a decoupling between these two stages. And then what we have is essentially in the second stage, which is the retraction and takeoff stage. What we have is that the driving force is capillary, because we have a surface tension with surface energy which is quite high because of this pancake shaped droplet, and hence the driving force is capillarity, which we can give by this scale of gamma times r. And then, of course, that reminds us of this very nice work once again from like several people, but also this one. The second one is from David Carrez and Christopher Klein's group, and this paper, this observation was first made by Jonathan Bodeko in this PRL in 2009, which is the coalescence-induced jumping of droplets, because in there also, at t is equal to 0, you have this excess surface energy that has to go somewhere, and once we have this this coalescence and the droplet has excess surface energy, it's going to take off from the surface. And once again, the driving force in this process, that's capillarity, and that happens because of this excess surface energy. And the resisting force is viscosity, which we also see over here in our case. And what we can do is that we can write down this resisting force as this. And here, what we are trying to do is basically we are trying to draw an analogy between this drop impact, where you have this excess surface energy that leads to takeoff, and this coalescence-induced jumping of droplets, where once again we have excess surface energy and that leads to takeoff. And in both these cases, we will have a resisting force that is because of viscosity, and you can think of this force as a dissipative force because of coalescence type flow field, essentially. And then we can further simplify this by writing it as eta times the inertiocapillary velocity scale, because the driving force is capillarity, and times this radius, which is the length scale in this process. And the idea is that this radial momentum that happens when we have this radially inward velocity field, that is basically equal to this integral of this f gamma minus f eta, and that gives us some sort of radial momentum scale, and that we have over here. And that takes me to the second very big assumption that I'm going to make while making this scaling argument, and that's basically that when we have this radial momentum scale, we are going to assume that the vertical momentum scale that is created because of the substrate, because we have a substrate that creates an asymmetry, and it's going to direct the radial momentum into a vertical momentum, and then we are going to assume that these two momentum scales are the same. And this if you know about, let's say, these kind of analysis, you know that this is a very big assumption that I'm making as I write this correlation over here. And then, of course, the idea that when will this drop stop bouncing? It will stop bouncing when the rate of change of this vertical momentum that is smaller than gravity, which is here. Then the drop will not bounce. And this, by the way, is also related to the second impact peak that we saw in the previous talk, and that's how we got this idea about trying to come up with a scale of how much this dp dt would be, and then if that force that is coming from the substrate, if that force is smaller than the weight of the droplet, which is this gravity fg, then the drop will not bounce. And if we just plug in all the terms that we have collected on the previous slide, we get something like this. So gamma r minus, so basically capillary driving minus this viscous dissipation in some sense. And if that is of the scale of this weight of the droplet, then the drop will not bounce. And if we now fill in this velocity scale, which is this inertiocapillary velocity, then we end up with this relation, which is in the dimensionless form, looks very naive. That's basically this critical Onezog number plus the critical bond number. If that is equal to 1, the drop will not bounce. And as you can immediately see from this this very simple argument, is that it goes to both the asymptotes. So if the bond number is very small, then we have basically that Onezog critical is equal to 1. And if the Onezog number is very small, then we have that the bond critical is equal to 1. So both these asymptotes are basically the trivial limits of this very let's say simple equation that we arrived by making these all sorts of assumptions and all sorts of arguments about the drop impact process. And of course, if we plot this in this phase map of the bond versus Onezog, then we get this line over here. So now I'm basically plotting this that bond plus Onezog is equal to 1, and that's the line that you're seeing over here. And now if we plug in the data points from the previous papers, we get them over here. So it does go through this extra data point that we had from our previous work. But of course, just because it matches with the previous works doesn't mean it's accurate, because you still see that there are many empty spaces all over this line. And hence what we did was we ran several simulations. So for example, we ran this set of simulation for Weber number of 20, and we found this bouncing to non-bouncing transition given by this circles over here. And then we also changed this Weber number across from all the way from 1 to 50, and we saw this this transition which happens at pretty much the same very close to this line essentially. And this is spread that we see because of the influence of this Weber number that's narrow, but it's still present. So both this critical Onezog and critical bond number, they still have a dependence on Weber number, but most likely it's a second order dependence. So it's because all of these lines, they fall very close to this bond plus Onezog critical equals to 1 formula that we just derived. So with that, I come to the summary of this the second part, which was this: when will this drop stop bouncing? And essentially it happens when we have this Onezog plus bond equals to 1. This paper is currently under review, and this is in JFM, and we have already gotten some positive comments. So this should be in press very soon, but for now it's on archive, so you can read it from archive. So, and for this, of course, I would like to thank Pierre and Detlef, with whom I did most of this work. So with that, I come to this acknowledgement slide. So I promise that I will reveal the color code towards the end of this my talk, and the color code is the following. Essentially, everyone with orange over here are the theoreticians in the group, and everyone with blue are the experimentalists in the group, and I am somewhere yellow in between, which you don't see on the slide because I do simulations for them. So with that, I would like to thank you for the attention. I would like to thank the organizers for inviting me in. And of course, I forgot to mention, so we believe in openness in science, and that's why all the codes that I have used throughout this talk, they're all available on this GitHub repository. So you can just go there, use it, try to reproduce the results, and have fun with it. So with that, thank you so much.
Okay, thank you, Dr. Sanjay, for the very the interesting talk. So for our now it's the Q&A time. So for our audience, if you have a question to ask Dr. Sanjay, you can unmute yourself and ask your question directly. So any question from our audience? Yeah, maybe I can start with one simple question. And so I noticed that when you do the simulation, when the contact line decay on the surface, I see there's some oscillation motion in your simulation. Is this kind of opinion you're trying to model? For example, in a slide number 67.
Oh, okay. Okay, so that's way back. Let me see. Well,
Yeah,
I mean, first of all, it cannot be a pinning effect because in the simulations we don't have a contact line, because what we assume is that there is a thin air layer which is of the same order of magnitude as the grid cell, and that thin air layer is always present between the droplet and the surface. Let me do this. Let me just go out. So you said slide 67, I guess. Yeah.
yeah.
So and then we have this thin air layer between the drop and the surface, which means that there cannot be any pinning. Of course, what it also means,
if you pay attention to later the movie, the pinning area now is kind of oscillation. I'm not sure what's this kind of just wait 1 second.
That might also just be numerical errors.
You see here? Yeah, you see here.
I see what you mean, and that could just be numerical errors that occurs as this very viscous blob is trying to retract, and in fact, and that could just be some numerical errors that's coming in over there.
Okay,
but so by that time, the drop has already lost most of the kinetic energy because of the bulk viscous dissipation. And what's trying to do now is, because I think for this case the bond number is 0, so the drop is trying to go to a spherical shape, because that's the equilibrium shape, and then the flow velocities are quite small, and probably it's just numerical errors that occurs at that time.
Okay.
Yeah.
So
there's pretty much no kinetic energy is left, but there's still some residual, most likely some error, I guess.
Okay.
But what you see before the oscillation is indeed a dark region at the contact, like an apparent contact line, and that occurs because of indeed the wedge flow in the viscous dissipation that you see, and that could also be like a leftover part of that you see that we see as a some sort of oscillation. And also we should be careful, because what I'm plotting here is a log 10 of the viscous dissipation rate function, and this, since because it's log 10, so even tiny fluctuations, they are exaggerated because of this log there. So probably the values there are very small. It's like 10 raised minus 3 or so in these units.
Okay. So another question is, you show there's some experiment is done in the International Space Station. So for the droplet, actually, whenever you go to the space, the size can be huge. Usually on Earth we have the gravity effect, so the interface stability will be an issue if you go to a bigger size of the droplet. But in space station, you don't have this issue. So every time you do droplet experiment, you can go extremely large size of the droplet. I'm not sure if there's any measurement of the force to compare with the observation on Earth.
No, I don't think there is any experimental observation there. For sure, irrespective of the size of the droplet, the drop will be of bond 0 or very close to 0, because G is effectively 0. So the bond number would there be 0. And what would happen is that since we are going at much, let's say, bigger droplets, the Ohnesorg number will be very small. So even smaller than 0.001 that I showed you in the previous slides. So yeah, I agree. But if you see, for example, here, I mean, the droplet is, I guess, as the diameter of the droplet is essentially same as the eye of Scott Kelly. So maybe we ask him about his eye, and then we have a scale to measure how big this droplet is. But I don't know. I can ask.
Yeah.
We could probably ask. So it's on YouTube now. So maybe he sees it and then he answers us.
Yeah,
because I really don't know the size of this droplet.
Yeah, because for example, in your experiment, usually you use the size is in size of a millimeter, something millimeter.
1 millimeter, yeah.
1 millimeter.
But once we make it dimensionless, it doesn't matter. It's 1 millimeter or 10 millimeters. I mean, as long as we know what the numbers are.
Yeah. So another question is, you use the hydrophobic surface. So we know if you treat the surface, you can use some chemicals. And you can also generate some physical roughness to have the hydrophobic property. Is there any difference if you use chemical coated hydrophobic surface, or you use the physical structure roughness to generate the hydrophobic surface? Is there any difference for you to measure the bouncing force?
So let's say, I mean, so very briefly, I probably am not the best person to answer this, because I was not the one doing the experiments, and I personally did not check what are the effect of these different hydrophobic surfaces. But I know that if you make the super hydrophobic surface differently, I don't know if it influences the forces or not, but it definitely influences whether or not the drop will take off. Because, for example, during the impact spreading retraction stage, if you have this transition from KZ to Wenzel state, or the other way around, like one of them which impales the droplet will not bounce. Or if there's some irregularities that interacts with the droplet, and the droplet gets pinned, for example, at the surface because of some irregularities, or not making that super hydrophobic surface good enough, it's possible to have a bad super hydrophobic surface, and that can have some defect that can pin the droplet, and then once again the drop will not bounce. In fact, I was looking in the literature, and I think there are works from some experimental groups who find the transition from bouncing to non-bouncing at Onizog numbers of 0.2 even. For the same set of things that we are trying to do here, and which makes me wonder is that the limit that we find, this Onizog of 1 and Onizog plus bond equals to 1, that really is the upper limit if you were to have a perfect super hydrophobic surface, which doesn't exist. I mean, theoretically it exists, but if you assume that this air layer is stable enough that it doesn't go anywhere, it's always there, then you would get this upper bound that we find. But there are works in the literature where the hydrophobic surface is not good enough, and then the Onizog number, critical Onizog number, is not 1, but actually even 0.2 or 0.5 even. So we don't numericists, we try to avoid those, so that we can have.
So you mentioned the literature have the same setup as your setup. You mean just the contact angle is the same, but
what I mean is that they were trying to make super hydrophobic surfaces, and they're apparent. So if you make the observations in a static case, they're still the same. But once you start increasing the viscosity of the droplet, how is that gonna interact with the surface? We don't know that well. And then they do have there are cases where in fact it's also in our group. So in our group as well, one of my colleagues was doing these experiments, and he finds a transition at 0.25 Onizog number. But then you could actually see in the from the movies that the contact line got pinned at one of these defects. So it's really very tricky to differentiate between a critical Onizog number of 0.7 or 1 or 0.5 in the experiments. But I think the surfaces that we use, they have a shoot template, like they use shoot to make this the surface, like carbon shoot or something. But the details are there in the supplementary material. If you or I can put you in touch with the person who actually did the experiments.
Okay. Yeah. Thank you, Dr. Sanjay. Any other question from our audience?
Hello, hi, Dr. Sanjay. This is Xiao Yan from University at Buffalo. So thank you very much for the interesting talk. So I do have two questions. So first, I noticed that you have plotted the relation between the force, the impact force versus the contact, like the time. So, but meanwhile, I'm wondering if you have considered the deformation of the droplet, like the displacement, the relation between the force versus the displacement inside of the time. So because we know there are a lot of famous a contact theory, which tells us the relation between the force and the deformation or the displacement of the droplet. So I'm wondering, based on your numerical data and your experimental data, have you tried to compare those data with a classical theory to understand the relation between the impact force versus the deformation of the droplet.
So is this the Wagner theory that you're talking about, or is it something else?
It's just a general, for example, for your current cases. So I mean, you have all those kind of simulation data. It should be straightforward for you to extract the deformation.
I agree.
Right?
Yeah, I agree. So by deformation, I guess you mean the deformation of the droplet, right?
Yes.
So yeah, so indeed, actually, I don't think we tried it, but I won't be optimistic, and there is a reason why. Because if you assume the droplet to be like a spring mass system, as people do, that's how you would get this force as kx, so k times the deformation. That should give you some sort of force, right? Is that the one that you? So it's basically the spring mass analogy from David, Curry, and all.
Right.
Yeah. So, but there is a yeah. So there is a flaw in that assumption, and that's basically, let me bring out one of the, let's say, this plot here. So if you have like a spring mass system, right, the forces there are symmetric. So it's the same. So during the compression stage and the takeoff stage, you would get like a symmetric force curve, which we don't see here. So in fact, the force peak in both, let's say, the impact as well as takeoff, it's quite skewed to one or the other side. And in fact, if you just model drop impact with this force which comes in because of deformation, then you would think that there is only, let's say, two stages, like spreading and takeoff, and both of them should happen at, let's say, t/2 and t/2. But that's where the theory breaks down, actually, because we see that the spreading is 1/4 of the oscillation cycle, and the retraction and takeoff is 3/4 of the oscillation cycle. So there is an asymmetry between the impact and the takeoff phases, which is not at all captured by this spring, like this deformation versus force curves. And in fact, this is one of the, let's say, examples of where such a theory would fail, pretty much. And that's why we never tried comparing, because then again we know that it's not supposed to work. So
okay,
yeah.
I see. Yeah, thank you very much for the further explanation. And my second question is about the fluid itself. The fluid inside of the droplet. So you mentioned the fluid that you are studying right now lies between water and some kind of ink jetting, like a fluid, right? So so if you can go back to the very beginning, somewhere, yes, here. So I'm just wondering, so if we further push the limit of your study, like say currently you are studying the bursting bubble for your current system. So say if we want to use some fluid, like for the ink jetting printing, so what might be different between the two, like scenario?
Yeah. So in fact, so part of this work was also inspired by this inkjet printing collaboration that we have with Canon. So that's an inkjet printing company, and we work together quite a lot with them. And in fact, if you notice that some of the Onozog numbers that I showed were indeed here, which is indeed in this regime of inkjet printing. Of course, there you don't. The first difference is not just in the fluid, but actually on the substrate, because in inkjet printing, the substrate is paper, or paper coated with another, let's say, primer or something, and then it's not super hydrophobic anymore. So that's one major difference. The second one is in the ink itself. So the ink is not Newtonian anymore, and in fact, we still don't know what the ink is. So it has hundreds of components, because when they make ink, they are not making it based on the, let's say, simplicity. They make it by thinking about how much time it takes to cure it and so on. So there are many different reasons of why they would put something inside the ink, which means that the ink is quite complex. So it could have elasticity, plasticity, all sorts of, for example, surfactants that would also lead to Marangoni flows and so on. So for that, there is this this very nice annual review from Detlef, which came out this year, I think, and he goes in details about these things. And we in fact have a whole, let's say,
yeah, very good to know that. So yeah, thank you so much.
Yeah.
Okay, so any other question? So if not, we will stop here and thank Dr. Sanjay for his interesting talk. And then we will, yeah, thank you. Then we will meet you guys in next week.
Yeah, thank you, Sanjay.
Yeah. Okay.
Okay.
Thanks.